In today's video, we have a question which says that a wall of a furnace is made up of inside layer of silica brick 120 millimeters thick. So now if this is our wall of furnace, it's made up of inside layer of silica brick. So let's call this part to be our silica. 120 millimeters thick, covered with a layer of magnesite brick. So this is a layer of magnesite brick. So magnesite with a thickness of 240 millimeters. The temperatures at the inside surface of a silica brick wall and outside surface of the magnesite brick. So this is inside surface, 725 degrees Celsius. Then the outside of the magnesite is 110 degrees Celsius. The contact thermal resistance between the two walls at the interface is 0.0035. So we are talking of the thermal contact, the contact thermal resistance, right, between the two walls. So we are talking about this portion. Now, when you take composite walls, right, one of the assumptions was that there is no temperature drop between the two walls or between the two surfaces. Now, that is one assumption. Now, if there is a drop between the two surfaces, it means that at this surface, the surface separating or combining the two walls, there should be a temperature drop. Let's say there is a T1 here and there's also another T2 here. And then the temperature drop between them. The temperature here is not equal to the temperature here. That's what it means. So if you have any temperature at this point, let's say T naught, the idea is that there is a temperature drop from T naught to T1, right? And then if there is temperature drop between the two surfaces or between the two interfaces, then it means that from T naught to T1, there is a temperature drop, yes. And then from T1 to T2 at that same interface, there will be another temperature drop to T2 before a temperature drop will be somewhere here, T3. And now this becomes our composite wall. So this is the idea. But if there is no temperature drop, then we can see that at T naught to T1, there is a temperature drop. And at T1, there is a temperature drop to T2. And this, it means that at the interface here, there is no temperature drop. But now here, the question says that the contact thermal resistance between the two walls at the interface is this. Now, there will be a thermal resistance only when there is a temperature drop, right? So it means that from this interface to this, there is a temperature drop. And that temperature drop, let's call it T2, T3, because we don't know. And let's call this part to be our T1 and this part to be our T4, right? So from K, now let's call that part, now is thermal resistance. So R interface is equal to 0.0035. The thermal conductivities of silica, so Ks, is 1.7, and that of the magnesite, Km, is 5.8. Calculate the rate of heat loss per unit area of walls. Now, we know that from the composite wall we did, the rate of heat loss is actually the drop from this point to this point, from here to here, and then from here to here. So they are the same throughout. But then, so we ask ourselves, do we know T2? No. So if you had known T2, we can just go straight and evaluate the quantity of heat transfer from this point to this point. If you had known T2 and T3, we would have used that. If you had known T3 and then T4, you would have used that. But because we don't have them, we're not going to use that. But then realize that we have the overall temperature difference. So T1 and T4, we have them. And then we have their thermal conductivities too, as well as the resistance C. So you can see that our Q here is equal to overall temperature difference all over summation of our resistance. Right? So our summation of our resistances, we are going to get resistance of the silica plus interface resistance plus resistance of the magnesite. The resistance of the silica will be, because it's by conduction from this point to this point, by conduction is going to be T1 minus T2. Sorry, we are talking of resistance. We are talking of resistance, so it's going to be 120 millimeters, which is the thickness, all over Ke. So Ks times our E. Right? So we are left with 120. So we have to convert this to meters. Times 10 to the minus 3 all over Ks is 1.7 times E. And this is our Rs, resistance at the silica. And then our R interface. So from this point to this point, it was given in the question as 0.0035 per unit area, right? Means that it's per area, so over area. And then R at the magnesite will be equal to change in thickness, right? So 240 times 10 to the minus 3 all over Ke. So Km is 5.8 multiplied by the area A, right? We know that for conductors, thermal resistance is equal to change in thickness over Ke. So that's what we are using. So for Rs, this is our thickness, 120, and this is our Ks, our E. For Rm, this is our thickness, this is our Km, and this is our E. Right? So our overall temperature drop, our overall heat transfer rate is equal to the temperature overall, which is 725 to 110, so 725 minus 110, all over summation of the resistances. So 120 times 10 to the minus 3 all over 1.7 E plus the interface 0.0035 all over E plus the magnesite 240 times 10 to the minus 3 all over 5.8 E. You like that they all have E's, right? And then we don't have the area. The question wants us to find the rate of heat loss per unit area. So we can factorize our area out. And then we having Q equals 725 minus 110 all over 1 over area out 120 times 10 to the minus 3 all over 1.7 plus 0.0035 plus 240 times 10 to the minus 3 all over 5.8. Now 1 over A comes up, right? So we are going to get Q is equal to A multiplying 725 minus 110 all over the summation of the resistances. So let me point that 120 times 10 exponent minus 3 all over 1.7 plus 0.0035 plus 240 times 10 exponent minus 3 all over 5.8. So we get 0.11547. Now we want the heat per area, so you can divide 2 by the area, right, and get Q over E is equal to 725 minus 110 all over 0.11547. And this will give us 725 minus 110 divided by 0.11547. And then we're going to get 5326.17 watts per meter squared. So our I is the heat transfer per area is 5326.17 watts per meter squared. Now the second part is that we should find the temperature drop at the interface. So now we need a temperature drop at the interface. And the temperature drop here refers to this portion, right? So there's a temperature drop here, and then we need that temperature drop. So we can either find T2 minus T1 straight away, or if that isn't possible, then we have to find T2 separately, find T1 separately, and then we subtract them, right? So now you have the overall heat, we have the heat, and then this heat is actually equivalent to the heat drop from this point to this point, and it's equal to that drop from this point to this point. So now we can equate this and see that our 5326.17 is equal to the heat drop from here to here, which will be T2 minus T3 all over the resistance, right? Because we know that our heat is actually equal to temperature drop all over the resistance, right? And then we put our thermal resistance there. So the resistance at the interface was 0.0035. So we put that there, T2 minus T3, and equate them. So we are going to get 5326.17 times 0.0035. That will give us 5326.17 times 0.0035. We are going to get 18.64 degrees Celsius. So now becomes our temperature drop. Now, how do we validate that? Or how do we know that that is correct? So we can also try another method. We can either find T2, find T1 separately, and then we subtract them. And let's see if that will give us the same answer or even very close to the answer. Right. So in finding our T1, we can just simply say that our 5326.17 should be equal to T1 minus T2, right? So 725 minus T1. Because the same heat which is being lost from moving from T1 to T2 all over. The resistance here is a thermal conducting resistance, right? So we change in X over K, and then our change in X is 120. So 120 times 10 to the power minus 3 all over our K, 1.7. It's per area, so the area will multiply this and then everything cancels out. So we are going to get 5326.17 equals 725 minus T1 all over. So evaluating that, 120 times 10 to the power minus 3 all over 1.7. So that is 0.0706. So T1 is equal to 5326.17 times 0.0706. So 725 minus T1 is this. And our T1 will be 725 minus what we'll be having here, right? So when I punch that, 5326.17, so minus 375.96. So we get T1 to be 349 degrees Celsius. So it means that the temperature here was actually 349 degrees Celsius. So T1, we can write it here, 49 degrees Celsius. Now let's find T2. We can use the same approach also. So T2, we can see that that same 5326.17 should be equal to. So now we have our T1. We can just repeat that. But I don't want us to use the root. So now let's use this. We need to find sorry, what you found was T2 rather. So let me put it there, T2, right? So T1 is for this portion, which is the 725. So T2, right? So we want to find T3. We can use this too. So T3 minus 110 degrees all over the thickness. So the thickness was 240 times 10 to the power minus 3 all over the K, 5.8. And then when we do that, we are going to get T3 to be 5326.17 times this value, right? So let me evaluate that value. 240 times 10 raised to the minus 3 all over 5.8. I get 0.0414. Then I can add the 110 to it. So I get T3 to be 5326.17 times 0.0414 plus 110. So I get 330.39 degrees Celsius. Now our temperature drop is equal to T3 minus T2, and that will be 349 minus 330.39, and that will give us 18.61 degrees Celsius, which is almost the same as this. So if you don't want to go through all these stress, you can just evaluate it using this, and you're still going to get the same answer.